Hi, welcome to Introduction to Machine Learning. Today we'll be learning about random forest. First, we will learn the theory and then we'll implement it. This lecture will be slightly long because I have taken a lot of effort to make sure that you understand the numerical implementation of random forest properly. Because if you don't understand that, you will not appreciate the way we are implementing it using code later. So let us take it a little bit slowly, but this module hopefully will comprehensively give you a proper understanding of what exactly is random forest. So this was a conversation that I had with one of my good friends a few years back. So he said that his AI company, so he was working as an AI head in his company. It was a heavily funded startup. And he said that the kind of AI solutions he is providing to his customers, which makes them very happy, are under the hood very simple. Apparently, they are mostly using simple regression model or XGBoost. And at that time, I knew what regression was, but the concept of XGBoost was not very clear. Then I started learning about XGBoost, and that's when I stumbled upon the idea that models like decision trees, which is the basic unit inside XGBoost, are very powerful, not just for academicians, but in actual industrial scale problems. So if you want to understand XGBoost, you have to understand decision trees. And decision tree we have comprehensively covered in one of the past lectures. So today we'll be looking at one more level deeper, which is random forest. We'll also, of course, do a recap of decision trees. So don't worry if you don't have the patience or time to go through decision trees once, but we'll go through it slowly. So let's travel a little bit back to, I think this is a French mathematician named Marcus de Condorcet. I don't know how to pronounce his last name, but he has a Condorcet's jury theorem, which states that if every single individual in a voting system has an individual probability that there will be more than 50% correct, then the collective probability of the group making a decision through a voting system will be higher than 50%. Basically, having a lot of people who can, on an average, make correct decisions more times than they make wrong decisions. Meaning, if a person is saying that, okay, this person is the right person to rule, or this person is not the right person to rule, and more than 50% of the times, if they are correct, and then you pool a lot of individuals like that into one group and let them vote, and then the probability that this collective voting has resulted in a good outcome or in a correct outcome will be greater than what any individual can do. So this is Condorcet jury theorem from 1785. Now, how is this theorem related to random forest? Before going into that, we have to do a small recap on decision tree. Only then you will appreciate why this Condorcet jury theorem is very important. So here you have a data set which has three types of animals: cows, pigs, and dogs. You have two features, weight and height, plotted on y and x axis respectively. And here it's like a three-class classification. You are classifying based on these two features. We can perform the classification using a decision tree, where you start with a first node. In the first node, which is also called as root node, the entire data set is available. Then you decide how to split this node into two children, basically two child nodes. And for splitting, you are selecting one feature and a threshold for that feature. And here the best feature to use, which I will explain why, is height, and the threshold is greater than 90 centimeter. So height greater than 90 centimeter means it's as if you are drawing a vertical line here, and all the data points which belong to the right side of this. So all these data points will go to the branch which is true, which is where this condition of height greater than 90 centimeter is true. And all these data points where height greater than 90 is false will go to the other branch. So the data set will get split into two parts. So that is what you see here. Now this data set on this node is called as a pure leaf, this node. And the reason is that the entire data set belongs to one class. It's simply, I think this is what, cow. So there is no need to split this node anymore, because splitting this is not going to segregate the data set anymore, because it's already belonging to only one class. But there is a scope for splitting this data set further. So you can now split using a different feature where weight greater than 120 is the feature. Weight is the feature that is used. 120 kilograms is the threshold that is used. So how does that happen? Weight 120 means you are essentially drawing a line like this. So now this data set will get it split into two parts. One part where weight greater than 120 is true will be this. Another part where weight greater than 120 is false will be this. So the true data set will go to the true branch where you will see these data points. The false will be the remaining data points. Now here, this node, which is a final node, there is no more branches coming out of it because it is a pure node. There are only data sets belonging to one category, and that category is dog. Green is dog. But if you look at this node, here also you don't see any branches coming out of it any further. So whenever there is a node with no more branches coming out of it, it's called as a leaf node. And the leaf node, if it only consists of data set of one type, it's called a pure leaf. So this is pure leaf and this is pure leaf. But this is an impure leaf because this has data sets belonging to belonging to both categories, pigs and dogs. But what prediction will this node make? The prediction made by this node is always that whatever data set ends up here, this will say it's a cow. So this node says that the prediction is cow. This leaf node, this pure leaf node says the prediction is green is dogs, right? So this will say that the data is a dog. Green is, yeah. And what about this node? Here it's like a democracy. So you predict based on whichever data set is dominating that node. So here blue is dominating, blue is pig. So this will say that it's a pig. Now, how do we make a prediction using this decision tree for a new data point? Let's see. So I can draw a new data point. So let's say a new data point is over here. So I'm drawing it somewhere here. I don't know whether this is a dog or cow yet or pig yet, but this is a new data point. And let's say the height equal to 125 centimeter and weight equal to 145 kilograms. I just know this. I don't know what animal this is. I just know the two feature values. Now, how do we classify this animal into one of these three categories using this decision tree? So first, go to the root node. In the root node, what is the condition? Height greater than 90 centimeter. Is my height greater or less than 90? Let me bring the data here so that it's easier for us to look at it. So the height is greater than 90. So this condition is true. So you are now going to traverse to this branch. And what does this branch lead to? It leads to a leaf node, which means the prediction will be cow. So this animal is predicted as a cow. What about an animal with height equal to 80 centimeter and weight equal to 60 kilograms? How about this? Is this a cow, pig, or a dog? Let's see. So height greater than 90 centimeter is false. So you have to traverse the false branch. Then here you will reach in this node, the condition that is being used is weight greater than 120 kilogram. Is weight greater than 120 kilogram? No, that is also not true. So you traverse the false branch again and you reach this node, and this node's prediction is dog. So now this data point, which is not a data point which was present in our original training data, this will be predicted as a dog. So now this is the idea behind how a decision tree can do a classification. It can also do regression. I will talk about that when we get into the random forest. So your question could be, what is the problem with this? It's classifying, right? It's working. The problem is that although decision trees are interpretable, because the branches, the way branching is made, there is some meaning. You know which feature is used, what's the threshold used. So its interpretability is very high. The problem is that they are very unstable. Unstable with respect to what? With respect to the data set. So here is an example. This example is borrowed from MLU Universe, Machine Learning Universe. I will show you that website in which they have an amazing interactive module about random forest. Also, they have a module about decision tree. It's really, really fascinating. I highly recommend you to check it out. I'll share the link. But what they are showing here is, look at the data set. So this data set consists of 3 type of trees: oak, cherry, and something, if I remember correctly. Here also you have pretty much the same data set, but what they have done is, for this, let's say data set 1 and data set 2, they have 95% of the data is the same, but 5% they have changed. In the training data, they changed 5% of the training data to have some Gaussian noise. So although the data set is almost the same, look at the difference in the structure of decision tree. So for sample 1, the decision tree structure is something that looks like this. The threshold values are different at different nodes. The feature that is being used. So here, I think there are 2 features. One is height and one is diameter. H is height and D is diameter. So they are using thresholds for height and thresholds for diameter for splitting the data at every node. So sample 1, perturb sample 1, tree created using the perturb dataset sample 1 and tree created using perturb dataset sample 2 are very different, as you can see from the structure. Even more drastic is the perturb dataset sample 3 and sample 4, the tree corresponding to that. So this tree corresponds to the tree that you get when you use perturb sample 3. It's still 95% pretty much the same data, except some perturbations have been made. But look at this tree. Here also, the data set is only 5% different. Look at the difference in structure between third and fourth tree. They are very, very different. What this shows is that decision trees are exceptionally sensitive to the input data set. The structure can completely change based on how the data set is. So this is not good, right? Because your underlying structure of your ML model should not be so sensitive to data set. I completely understand that it is depending on the data set, but if it is so sensitive, then you might have a problem when you are trying to make predictions using just one tree. So now this is the problem, right? This is the problem with just using a single decision tree. So the solution is what? The solution is to look at something called as ensemble models. Ensemble models it's like a concept where instead of using one machine learning model, you pass different data samples to different machine learning models and let them learn some patterns from the data set. Now, if you are provided with a new data, a test data, that test data you can pass into sample 1. The sample 1 is sample 1 of the data. So in training, the way it works is the training data set is split into different samples, or you can feed the same thing also. In decision tree, training data is split into different samples and each sample trains a model. So now you have n different models. Each model makes a prediction and then you aggregate the predictions made by the model, right? So if it is a test data, the test data will be just one data point, let's say. It will be fed into model 1, model 2, model 3, model 4, etc. Each model will make a prediction saying, okay, this test data is pig, this is dog, this is cow. And if majority of these models say that it's a cow, then you say that you aggregate and say that it's a cow. It's as if you are voting. In a democracy, in voting, a candidate wins if they get the majority share of vote. And same thing happens here. So if most of the models say that the data point corresponds to a cow, then you say that it's a cow. So this is called as an ensemble model. Random forest is a classic example of ensemble model because instead of using one machine learning model, which is decision tree, you use a collection of decision trees to make your prediction, right? So that is where we formally begin this lecture, excuse me, on random forest. It is a powerful ensemble learning algorithm. So you construct, you split the data set. I will walk you through the steps, but basically you have multiple decision trees making decision for you. So I will show you the ML universe interactive module so that we can play a little bit with random forest consisting of various number of trees. So this is the machine learning universe website, web page about random forest. And I want us to focus on this part. Just look at this number of trees 1 and tree accuracy. So let's do one thing. Let us change the number of trees. So here I'm scrolling down. Actually, there is a bar. Yeah. So here you can play with the number of trees in your model and play with and have a look at the accuracy. So let me keep the individual tree accuracy at maybe 60% is fine. And if you have just one tree, obviously the accuracy is going to be 60% because individual tree has an accuracy of 60%. But what if you have two trees where each tree has an accuracy, or three trees here where each tree has 60% accuracy? Then you have a collective accuracy increasing to 65.65 or 65%. So none of these individual trees have 65% accuracy. They are only each 60% accurate, but collectively, these set of trees now can make a better prediction at a 5% increased accuracy. What if I have 11 trees? See, accuracy has increased from where individual trees have 60, but the collection has 75%. And if you have 25 trees, you go all the way from 60% to 85%. It's a drastic improvement in accuracy. And you can see that to reach close to 99% accuracy, your individual trees need not be that accurate. Individual trees just need to be 67% accurate. But this random forest consisting of 25 trees can make predictions which are 96% accurate. It's fascinating, right? Because and this is what Condorcet jury theorem also mentions. Like, if each individual in a population can make a decision which is greater than 50% accurate, then the collective decision making power of a set of individuals who's voting to make a single decision for the group, that decision, there is a higher probability that that will be correct. And here, let us do one more thing. Just decrease the individual tree accuracy. You see what's happening when you decrease the accuracy for one tree case or two trees or 25 tree case. It's all decreasing, but you still see that the more number of trees you have, the more your accuracy is. What if this is 50%? If 50% is the accuracy of every individual tree, then there is no advantage, because there is an equal likelihood that the tree can make a correct decision or wrong decision, and that mistake will get propagated irrespective of whether you use 25 trees or one tree or five trees. What if the accuracy was less than 50%, which is not shown here, which means the group may collectively make an entirely wrong decision? Because if a tree is making 30% decisions, only 30% decisions correct, it means it's making 70% of the decisions wrong. And maybe that will also propagate. But the thing is, a model that makes 70% wrong predictions is probably a really bad model, because then all you need to do is like flip whatever predictions it is making to have 70% correct predictions. So generally in binary classification models, the worst models are ones that make 50% prediction accuracy, because a random coin toss, let's say you give a monkey a coin and let the monkey toss the coin, and then it comes up with an outcome. And if you use that outcome to make a prediction using your decision tree, that also will have a 50% accuracy if it's a binary classification. So in binary classification models, like in this one example, 50 is the lowest. So that's why you see here 50% being the lowest. But you see the power of having multiple trees. Okay, so now let us get back to what we were discussing about decision trees, about random forest. So there are a few steps involved. So first thing is, we should know that the data set that we have for training will differ from one tree to another, because there is no point in having all the trees make the exact same prediction. So if the structure of every single one of the tree in these 25 trees are the same, they are all going to make the same prediction. So how do we prevent the trees from making exact same prediction? What we can do is let each of those trees train on different data set and on different features of the data set, such that the structure of those trees will inherently become different. So the reason why this tree looks like this and this tree looks something different is because they were probably trained on different set of data and different set of features. So if you have 100 data points, you will probably only select a subset of that, a random subset within that big data, and you feed that to the first tree. And if you have, let's say, 10 features, you take another random subset from among those 10 features and you feed that to that tree. And like this, you repeat for many different trees. So that way, each tree can make a different set of predictions. So bootstrapping, the first step in making a random forest, is randomly selecting training data subset with replacement. What does it mean by with replacement? With replacement means the fact that you selected a data point in the training data subset for the tree number 1 does not prevent you from using the same data point for the next tree. So although you are drawing some data set to make the subset of training data, you still have the ability to draw the same data points for another tree. It's It's just that it has to be random. The process of drawing data to make the subset has to be random. Same thing you do for feature. So feature selection is, so bootstrapping means you create a subset of data, training data for a tree. Feature selection means you randomly choose a subset of features for each individual decision tree. And then you construct the individual trees based on finding at every node what is the right feature and what is the right threshold to use. We will discuss this in detail in a few minutes. And then what we do is we try to make a prediction, combined prediction or aggregate prediction, where each tree in the forest makes, let's say if it's a binary classification, each of them makes a binary prediction. And then depending on the majority prediction, whatever the majority is saying, you say that is the final outcome. That is the collective outcome of these group of trees. So this is the essence of random forest. And I want to play a little bit with you using a numerical example so that you can better appreciate random forest. So let's say you have 5 data points. So you have a data set consisting of 5 data points. So this is data set 1, 2, 3, 4, 5. So each row is a data set. And for these data sets, you have 3 features. Feature number 1, which is A, feature B, and feature C. Each feature can have 2 values. I'm just taking this as an example. I know it's very simple, but you will understand the gist of building a random forest using this. So each data point has 3 features, A, B, C, and each feature can have one of the 2 values, 0 or 1. So that is what you see here. And then the final target, which is the prediction that you have to make, it is yes or no. So this will ultimately be a binary classification problem. So let us go through each steps. So bootstrap sampling means you are creating dataset subsets, right? Subsets of data. So first thing we have to decide is how many trees are we going to make? In this example, we will create 3 trees, and we will use those 3 trees to make a collective decision. So our random forest in this example, let's say it consists of 3 trees. So now we have to create a subset of data set, right? So let's say a subset consisting of data point 1, which is the first row. So this is the data point 1. So when I say instance 1, it means this entire row. Instance 3 means this entire row. Okay. So now imagine that the first tree in the random forest gets a subset of the data, which consists of instances 1, 3, 5. Second one gets 2, 3, 4, and third one 1, 2, 4. Okay. So this process is random. So the way you withdraw 1, 3, and 5 from this list of 5 data points should be random. But let's say for the sake of numerical example, this is the way subset is created. Then we have to create a subset of features for these trees, right? So now this is feature subset. And in the feature subset, let's say tree 1 is fed with the features A and C. Because you have 3 features, you can't select all the 3 features. Similarly, you can't select all the data points to be fed into every tree, because then every tree will learn the same thing. Similarly, all the features cannot be used for every single tree. So you have to select a subset. So here you are making subsets of length 2. So first tree will get A and C, second will get B and C, and third will get A and B as the features. Feature values are 1 or 0, if you remember. Now, let us see how the tree 1 will look like. So here what I have done is, each instance, I have denoted a color based on the target. So yes means I will put green color, and no means I will put red color. So green, red, green, this is red, and this is green. Okay. So I have data points 1, 3, and 5 going into the tree number 1. And what are the features I'm using for tree number 1? Only A and C. B is not there. So only A and C is the features, subset of features. So if instances or data points that we are using for tree number 1 is 1, 3, 5, all 1, 3, 5 are belonging to the same category, the green category. Why? Because all of them, the target variable is yes. So this is instance 1, this is instance 2, and this is instance 3. All of them are yes, which means you in fact don't even need to make a split, because this is already like a leaf node. It's a pure leaf because all data points belong to only one category. So although I have drawn a split like this, in theory, you don't have to split. And what is the prediction made by this? It's yes, because even if we use the feature saying, okay, a equal to 1 is a is the feature and a equal to 1 is the threshold, it will still split like this only, because you are not going to be able to split this any further by using a. So basically the prediction made by this tree will be at this node, it says yes, meaning whatever data point travels through the tree and reaches here, the prediction made by the tree will be yes. Now let us look at tree number 2. Tree number 2 has a subset 2, 3, 4 as the data points. So 2 is this row, 3 is this row, the entire row, 3 is this, and what? 4, right? This, the 3 rows in the middle. So it is no, yes, no. So 2 of them should be red and 1 of them should be green. So that's what I have shown here. 2, 3, 4. Instance 2 and 4 are red, which means no is the final prediction. The label of those 2 data points. And 3 has a label of yes, which is why I have shown it in green color. And we are not going to use feature A. We only have features B and C available. So here, if we use feature B equal to 1, so feature B and 1 as the threshold, equal to 1 as the threshold, the data points which satisfy this condition will go here. The data points which does not satisfy the condition will go here. So let's see for which data sets in 2, 3, 4, B equal to 1 is not satisfied in the data. So in the data, B equal to 1 is satisfied in 2 and 3. B equal to 1 is not satisfied in 4. So 4 will go to the no branch and 2 and 3 will go to the yes branch. So that is what you see here. Now this node, we don't have to split anymore because it's a pure leaf. There is only one data point and that data point belongs to obviously only one category. And since this is a green, meaning yes, the prediction made by this node, which is a leaf node, pure leaf node, will be yes. But now there is a scope for splitting this further. And for splitting this, we will use the feature C and C equal to 1 as the value. So let's look at instances 2 and 3, which are rows 2 and 3, in which C equal to 1 is satisfied by only this guy. So third, instance number 3 will go to the yes branch, as you see here. And instance number 2 will go to the no branch. So now you get 2 more leaves, which are the children of this node. So this leaf will make a yes prediction and this leaf will make a no prediction. All right. So that is the tree 2. And tree 3 uses features A and B. C is not used. And that has the subset data, which is 1, 2, and 4. And 1, 2, 4 means 1, 2, 4, these 3 rows. And we have A and C, right? So we use A equal to 1 as the threshold. And we check for which data points A equal to 1 is true. A equal to 1 is true for this row. Among 1, 2, and 3 rows, 1, 2, and 4 rows, A equal to 1 is true only for this. For remaining, A equal to 0 is the thing. So one data point from instance 1 will go to the yes branch, and 2 data points, which is instance 2 and instance 4, will go to the no branch. You can see that here. 2 and 4 went to the no branch. 1 went to the yes branch. Now this node and this node are both pure leaves, and this will predict yes, and this node will predict, this leaf will predict no. So now these are the individual decision trees and the predictions that they make in the random forest. Now, are we done? No, we are not done yet. We have to make prediction for a new instance. So now consider we have a new instance where A equal to 1, B equal to 1, C equal to 0. We want to make a prediction. So now we have a new data set, A equal to 1, B equal to 1, and C equal to what? 0. We don't know whether this is yes or no. This is yes or no. I don't know. But this is a 6th data point and we want to make a prediction on this data point. How do we do that? Let's go through tree number 1. Tree number 1 has access to features A and C. So first it will ask you whether A equal to 1 is correct or not. Is it correct? Yes, A equal to 1 is correct. And tree 1 will say it is yes. So let us write it down. Tree 1 made a prediction that it is yes. Okay. What about tree 2? Tree 2 will first ask, is B equal to 1 true? B equal to 1 is true, right? So then it will go to this branch. Then it will ask, is C equal to 1 true? C equal to 1 is not true. C is actually 0, which means it will go to this branch and the prediction made by tree 2 will become no. So although tree 2 looks complex, the prediction is exact opposite of what tree 1 predicted. So tree 2 will say no. What about tree 3? Because now the democracy process is such that if tree 3 predicts yes, the overall prediction will be yes, because 2 trees will then say yes, and 1 tree will say no. But if tree 3 says no, no will be the final answer by the combined random forest. So we pass A, B, C, 1, 1, 0. And here the question is A equal to 1? Yes, A equal to 1, correct. which means you go to this branch and the prediction of this branch, I mean, this node is yes. So tree 3 will also make the prediction yes. Tree 3, yes. So yes wins because there are two yes and one no in the democratic voting process. So I have just denoted the branches that made the decision. So for tree 1, this was the branch that made the decision for yes. For tree 2, this is the way in which it reached the decision no. For tree 3, this was the way it reached the decision yes. So yes, yes, and yes, no, and yes. So yes survives. So the final aggregate majority voting result is that the verdict by the random forest is yes, right? So this is a very simple numerical example using which you can understand how a random forest works. I also want to spend a little bit of time with you on this random forest module by MLU. So let's do that. Okay, so now let us see this one section where the model predictions for random forest and model prediction for individual trees are provided. So here you have 1, 2, 3, 9 trees, 9 separate trees, and in the image, but there are more trees that they use in the module. And here what you see is the predictions made by the trees collectively, okay? And so if you are looking at just one tree, what you see here is that the trees are making a binary classification based on 4 features. So let's ignore the fact that there are 4 features and all. Those things are not important. What is important is this. How many data samples did the tree make a right prediction? Right, that is the question. So here you see the predictions made by the 9 tree for a given data point. So this one column corresponds to one data point. And if the color is this shaded blue, it means that one tree made a wrong prediction. If the color is filled color, it made the right prediction. The prediction itself could be no or yes, right? So the fill will appear only for one color because it's the prediction is it's either no or it is yes. Only one of them can be correct. So the first tree, when I hover my mouse pointer here, the first tree will get highlighted and you will see the branch which led to the decision. And the decision was wrong, which is why it is showing like a shaded color. Here, the tree made a right decision. It predicted no, and that was the right decision. You can see the branch which led to that. And similarly, if I move my mouse pointer, you will see the decisions made by all the individual 9 trees here. And the forest makes a wrong prediction here. And why is that the case? Because the majority of the trees made the wrong decision, and the forest is going to take whatever decision the majority says. So I think what the majority said here in this case is no, because only if this guy says, yes, only if this says yes, this says yes, 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 yes. Only in that case you will get an incorrect prediction, right? So here, while the correct answer was no, majority of the trees predicted yes, which is why forest also made a wrong choice. Let us look at the next data point. Next data point, the right answer is yes, which is made by 1, 2, 3, 4, 5 trees, and remaining 4 trees said no, which means the forest said yes, and forest made the right answer because majority of the trees made the right answer, which means forest also got the right answer. For the next data point, except one tree, all the other trees got the right answer, which means forest also got the right answer. For the next data point, all the trees got the right answer, which means obviously forest got the right answer. Here also all the trees got the right answer except one. The right answer here is no, and forest got it right. So that is, and here you see the number of correct predictions made by the forest. I think there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, around 30 data points or something. I haven't counted it, but I think it's written somewhere here for sure. There are around 30 data points, and the forest is making only one wrong decision. But for all the other data points, it is making the correct yes or no prediction. But now let us look at any individual tree. Is there any individual tree which is making one prediction wrong and all of the other predictions correct? Let us see. So the first row, this is one tree. These are the predictions made for the 30 data points for one tree, the tree number 1. And you can see that this tree has made 2 mistakes. Remaining all are correct. What about this tree? This tree has made, in fact, only 1 mistake. Remaining are correct. So this second tree is actually as good as the random forest in purely in terms of the prediction accuracy. It even got the one which random forest made a wrong guess. This one got correct. So, but overall accuracy, random forest is still better. still better or comparable to the second tree. But look at all other trees. All other trees are making more than one mistake. So this tree in this third row, it's making many, many, many mistakes. So this is a very bad tree. So this is the best tree among all, because that tree is making all correct decisions except for this one data point. It made a mistake. I don't see any other tree here where only one mistake is there. One row is one tree, by the way, because you see when I'm hovering my mouse pointer over one row, the highlighted tree is not changing. So if I'm moving only over the first row, you see the only first tree in these 9 trees in the image is getting highlighted. So this shows that random forest, because it collectively makes a decision based on the decision made by majority of the trees, it gets correct. It gets more correct decisions on an average. And the color is easy to guess, because if majority of the trees in the forest said yes, then collective decision will be yes. Otherwise, no. If majority makes a mistake, then forest will also make a mistake, which means the worst tree in this is the first tree, because this tree has made no, sorry, the worst tree. No. The worst data point on which all trees are getting wrong answer is the first data point, because here on this data point only 3 tree got the right answer. Worst tree, in fact, is, I would say, tree number 3, right? Because this guy has almost all of them wrong except 1, 2, 3, 4, 5, 6, 7, 8. Some 1/3 of the data points this guy has got wrong. So in my opinion, it's not my opinion, it's based on the data. Based on what I can count here, it looks like this is a really, really bad tree. This second tree is a really, really good tree. Last tree is also looking very bad because it's making a lot of mistakes. So this tree also is very bad according to what the data in this table says. So this is a way to kind of visualize. Just play with it. Read the text in this blog article. It's a very beautifully written article. I highly, highly recommend it. Just spend 10 minutes. It will be a very, very good investment for understanding random forest really well. Okay, but I hope you understand the working principle of random forest. It's like a majority's decision. Now let us implement random forest from scratch. So here I'm going to implement it in Julia, not in Python, simply because I'm following this part of the lecture in the machine learning introduction in Julia course. But the logic is very much the same. I'm not using any complex functions at all. So the exact same logic you can follow in Python also. So feel free to use the language of your choice. But before going into the code part and before explaining the code to you, because the code is a little bit long, it's simple but long. I want to think together with you the algorithm that we are going to follow, because if we have the clarity in algorithm, it's much more easier to follow the code. So first, let us discuss the data set a little bit. The data set is like this. You have here you have 100 data points, and each data point consists of 2 features. Feature 1 plotted along x-axis and feature 2 plotted along y-axis. And you are making a binary prediction, binary classification, 0 or 1. So he's 0 here, I have denoted in blue color, and orange is 1. So it's like a yes or no classification based on 2 features. Now, the test data would look something like this after we finish running the random forest algorithm, where you will have random data points, and you can see that it's mostly making right predictions, because here the way data set is divided is such that some line is there here, right? A line is there somewhere here, such that most data points here belong to category 1 and most data points here belong to category 0. But there are some exceptions. But if a test data point belong here, it categorically, it should belong to this, because that is what the data set looks like. That is what the decision tree should ideally predict. And you can see that it's kind of predicting that. So let's see how to implement all of this. But before going and explaining this code and before running it, let's think about what all things are involved. So first, we need the data set. So we have the data set, which consists of instances. So if we have 100 data points, we will have 1, 2, 3, etc. up to 100, right? And each data set has 2 features, feature 1 value and feature 2 value. Each feature value are from -3 to 3, -3 to 3. Yeah. So each feature will have some value. This could be -2.5. This could be 3.0, like that. So different features, 2 features and different values. And here there is a label, which is 0 or 1. So this could be 0, this could be 1, this could be 0, 1, 1, etc. up to 100th. So now each data point is one row. This is one data point. This is another data point, like that. Okay. Now what we are going to do first is we will split the data set into training and testing. So first define the data set, and then we have to do train test splitting. And splitting meaning you will only choose some of the rows here. Maybe 80% of the rows you will use for training, 20% of the rows here you will use for testing. After splitting, we have to construct individual trees in the random forest. So before that, we have to decide how many trees, the number of trees in the forest, and the depth, maximum depth of each tree. And what is depth? Depth is this. So here, this is 1, 2, 3, 3 layers deep, this tree. Here you have 1, 2, 3, 4. Fourth layer is the prediction layer. I mean, the number will be plus or minus 1 depending on where you start your counting from. But basically, you see the number of layers are how many times each branch, each node branches. Is it once? Then you have only one more layer created. If it is again and again branching 3 times, then you have 3 more layers created. So number of trees, number of layers in each tree, maximum number of layers. And you also need to know, or also need to specify minimum number of data points per node. So here you could say number of layers max is 3 or 4. You could say something like that. Here you say minimum every node should have 2 data points. If 2 data points are not there, then you're not going to split the node any further. So this you can specify. Then we will start implementing each tree one by one. So you need a variable for storing what? For storing the forest. And this forest will be bunch of trees together. So basically you will need a variable where you are storing individual tree. And within the individual tree, you need a variable where you are storing, because tree is consisting of nodes. Some nodes, one node is a root node, some nodes are in between nodes, and several nodes are the leaf nodes. So you need a variable for nodes, right? And then we will recursively, we will use a loop from tree number 1 till tree number 20, or whatever is the number of trees you are building. So, and each tree will be built. And how is it built? Because each tree will every tree get access to the entire training data set? No. So you have to split, create, for every tree, randomly draw a subset of training data and subset of features. So what is subset of training data? If 80% of the rows are the training data, within those 80%, how many are you withdrawing for training that tree? Maybe you will only choose 60 of those rows. Maybe you will choose only 20 of those rows from the training data. And what is subset of features? In this data set, you have only 2 features, feature 1 and feature 2. So subset means either you pick feature 1 or you pick feature 2, not both. So that is subset. And then you will have so now let us look at a tree level, right? So we will have a root node into which subset of training data, maybe 20 rows, and one of the features, feature 1 or something like that, is coming. And this is because of the example, but in complex example, there could be feature 1, feature 2, etc. There will be multiple features because your set itself will be very big, which means subset of feature will be not just one type of feature, there will be multiple features. But into this node, you will, let's say, have 20 data points. Now you have to decide how to split this node, which feature to select, and what is the threshold value. So you have to identify for every node best feature and best threshold. How will you calculate that? You calculate that using the concept of either you can use entropy reduction or information gain IG, or both are same. Entropy reduction is same as information gain, entropy, or you can use something called Gini impurity. Gini impurity formula is very simple. It's simply 1 minus sigma pi square. Pi is the probability of the items in one single node. So if every items in a node is the same class, then sigma pi square is 1, and 1 minus 1 will be 0. If every item is separate class, and then you will have maximum Gini impurity. So you calculate the Gini impurity to decide the best feature and best threshold. And based on that, you split the node, and then you have now left node and right node. And here also again you determine the best feature and best threshold. And when will you stop this? You will stop this whenever you have reached this condition, whenever you have reached either the maximum number of layers or minimum number of data points in that node. So if this node has only 2 data points, then you will not, I think you will split one more, but you will not split any more. So you will split at the place where you will stop the splitting when you exceed the minimum number of points required. I mean, you are below the minimum number of points required. You stop at that point. So this is one tree. Is that enough? No. Now you have to construct another 19 trees if you are constructing 20 trees. So you repeat the same process. Whatever you did, you create subset of data and subset of feature, and then you give it to the root node. From root node, you find the best feature and best threshold based on Gini impurity. Then you create the split, and if there are a lot of data points here, you split once again. As long as Gini impurity is reducing. If this is a pure leaf, then you can't reduce Gini impurity any further, which means you will automatically anyway split, cease to split, or you will cease to split if there are only a few number of data points, or if you exceed the tree depth above a maximum value. And then after that, you have, let's say, 19 trees or something, or 20 trees, let's say, and you want to make a prediction on the test data set. And test data set is what? Test data set are all these rows which were not part of the training data. Now you select a random candidate from the test data set with feature 1 value and feature 2 value. Okay. How will you make the prediction? Now you have 20 trees, first tree, second tree, third tree, fourth tree, etc. Right? So I'm just drawing random things. Now to the first tree, you feed this data. And this tree might make a prediction saying, okay, if feature 1 equal to less than 0.2, then predict this is yes, otherwise predict no. So feature 1, this tree will make a prediction saying yes. This might say no. This might say yes. Same data you are feeding into all the trees simultaneously. This tree might predict yes. And then if out of 20 trees, 11 or more trees make a prediction that it is yes, then you make a democratic decisions. So ideally, it's maybe better if this number of trees is odd number, so that there is no tie. So you can make a prediction, final prediction based on aggregate of all these individual predictions. So that is the final random forest prediction. Okay. So this is the algorithm that we are going to follow while implementing in the code. So I have, in order to save my time, I have already written the code. I have tested it. It's working perfectly well. So what I'm going to do is I have split the code into meaningful chunks, and I'll be walking you through these chunks one by one. And then we can write this whole thing in Julia and let us run it and let us analyze the results. All right. So first we import certain required libraries. This package is used for creating random numbers that will be forming part of our data set. Stats-based package is used for calculating the mode. Mode is like voting, right? In voting, you can find the majority by calculating the mode. Plots for plotting the results into this scatter plot. Then we have a bunch of functions, in fact, and we will be calling these functions only when we define the data set, and only after that we'll be calling the function. So initially we are just going through the definitions of those functions. So first, this is a function to simply calculate the Gini entropy at a node for a given threshold and for a given Gini entropy of a node for a given set of data which is there at that node. And then only we can know whether Gini impurity reduces or increases after we perform a certain split. So this function simply calculates Gini entropy. So it is 1 minus sigma pi square. So 1 minus sum of is sigma pi square. And what is pi? Individual pi is total number of things belonging to one class. So count map gives you the count of that particular value, and then dot divided by length of y means length of y is the total number of data points that are there in that one node. And this Gini impurity function will return the Gini impurity of that node, of the parent node before splitting. Then this is data splitting based on the feature threshold. So if this node has these many data points and you decide feature 1 greater than 1 is the, so feature 1 is the feature and 1 is the threshold and greater than, then whatever is true, those data, if these data points for which it is true, then it should go here. So these 4 should go here. And if for these 2 data points, this condition is false, then those 2 should go here. So the data set should be split into left node, left branch and right branch. So here that is what is happening. You have data set and labels X and Y, then feature that you're using and the threshold for that feature that you're using. So you have 4 incoming parameters into this split dataset function, and you are splitting into left or right based on whether the value of the feature is less than or equal to threshold. If it is true, it goes to the left branch. If it is false, it goes to the right branch. And you split using the same thing. You split not just X, but also Y, because X is the data, Y is the label. X means 2 features are there in the data. Y means the label, whether it's true or false. Okay, so that is the dataset splitting function. Now you have to find the best split, right? So this function, just because I have written it in this sequential order, don't think that we will be using this function or this function first. First, we'll be using some other function, but we need all these functions. So now we need a function also for performing split based on maximum entropy reduction or maximum Gini impurity reduction. So here we are using Gini impurity, not entropy. So please check that this is not entropy. So here we have to find the best split for a given data set X and Y and given subset of features. So X and Y is not the entire data. Please remember, it is subset of data. So first we say that the best feature, nothing. There is no best feature. There is no best threshold, meaning splitting is not possible. Current best Gini impurity is infinite, and best split also is nothing, meaning you can't find a better split. That is the initial assumption. And then we create a set of features in the feature subset. So 4 feature in feature subset means you have all the features one by one getting collected in this feature variable. Then you say for that feature, you can have different potential thresholds, right? So here thresholds equal to all the unique values that are present in the features. So this means if the features are some numbers, here you are collecting all the unique numbers. And then you say for threshold, for every single number in that threshold, if we use one number in the, so if 3.2 is the number that is present for feature number 1, we'll check, okay, for feature 1, if I use 3.2 less than or equal to 3.2 as the threshold, am I going to decrease the Gini impurity or not? So that is what we are going to test. So first we split the data set into left and right, X and Y. So X left, the data set on the left and corresponding labels on the left will be in this variable. Data set on the right and corresponding label in the right will be here. And then we check whether Gini impurity has decreased or not. So this if length, Y left length equal to 0 and length of the either of the right or left split is 0, which means further splitting is not possible, right? Then you skip this loop and you continue. If not, if the left branch and right branch has some number of data sets going into each, that means now you have to calculate the Gini impurity. So Gini impurity is calculated using this formula. And what is the Gini impurity? Gini impurity for the children node. Because Gini impurity for the parent node is different, for the children node is different. The collective Gini impurity is different. So that you can calculate using this, the number of points in the left node multiplied by number of the Gini impurity of the left child plus number of points in the right child times the Gini impurity of the right child divided by total number of points in the parent node. And then if this Gini impurity is less than the previous best Gini impurity, then you say that the new best Gini impurity is the current Gini impurity, new best feature is the current feature, new best threshold is the current threshold, and new best split is the current split. And then you recursively do this until you go through all the features and all the thresholds for a given feature subset and given data subset. And then you return the best feature, best threshold, and best split. Now, remember, this is just for one node. You have to do this for all the nodes in the tree. So still you are not you have not constructed any tree. You have simply, this function simply constructs one node, the splitting of one node. Okay. Now, this is the individual nodal structure. For every node, you need a feature that makes the split, the threshold of the feature that makes the split, which points are in the left, whether you have data sets going into the left, whether you have data set going into the right. And if the node is like a leaf node, what is the prediction that the node is making, right? Normally it will be nothing, because if it's a root, if it's not a leaf node, it's not predicting anything. So normally it will be nothing. All right. So this is not a function, it's just a structure in which we are storing the values of the individual node. Now, this is the function for building the tree node by node. So to build the tree, you have subset of data, x comma y. You have maximum depth here, and you have the current depth, whatever is the number of children that you have created from starting from the root node. Then you have minimum number of samples that every node should have. So these two things we predefined. So maximum depth, maybe you will say 3. Minimum samples at each node, you will say 2. Then you check, okay, is the length of the y, meaning number of data points, is it less than minimum samples? If yes, you are returning whatever node you have currently, which is a node, tree node where nothing, and mode of these data points. So what does this mean? It means nothing means there is no feature at the node, there is no threshold at the node, there is no left branch going from the node, there is no right branch going from the node, because this is a leaf node. For leaf node, these things are irrelevant. But for leaf node, a prediction is relevant. It has to make a prediction. And what is the prediction? Prediction is mode of all the data points in that leaf, which is why the last one is stats-based.mode of y, right? So it will return. But what if the maximum depth has not reached, or if you are not at a leaf node? Because if you were at a leaf node, this Gini impurity will also be 0. So either your number of samples are so small, or you have exceeded the maximum depth, or your Gini impurity is 0. In all of these cases, you return the node as if it's a leaf node. Otherwise, you go on to calculate the left and right split. So first you have to create a feature subset. Okay, so X and Y is not feature subset. I earlier said it's a subset, data subset. It's not subset, it's the data itself, because here we can create the feature subset. Or rather, okay, I might be wrong again. I think X, Y are subset only, but feature subset we create later. So feature subset is either we pick feature 1 or feature 2. So here the rule that you use is you use 1 by square root 2 that many number of features, whatever is the integer value of this. So if you have 10 features total, 10 by square root of 2, which is 10 by 1.414. And if this turns out to be some number, like we can calculate 10 by 1.414, 7.14. So you can use 7 features. So that is what we are doing. Totally that many features we will pick. And what else? Yeah, so the feature value, threshold value, and split value, right? So best split function was calculating what all. Best split function was telling us what is the best feature that we can use to split the current node, what is the value of the threshold for that feature that we can use to split the current node, and what is the left and right nodes, which is the best split. How does the left and right branch look like after splitting? So these 3 things we can get by calling the best split function. That is what we are doing here. We call the best, where is that? Yeah, best split function. And we get the best feature, best threshold, and best split. And then if the value of this best feature is nothing, meaning there is no feature that can give you a best split, it again means that you are providing a leaf node. So which means you return this as a leaf node. That is this command. Otherwise, you say the x left, y left, x right, and y right is the current best split. So you have the left branch label, right branch features, right branch label equal to the current best split. Current best split is whatever is returned by best split function. And then what we do is we return the node that we return finally is if the function did not return anything in the previous 2 if conditions. The final thing that we return is we return the best feature, we return the best threshold, and then we recursively call the function build tree. So here we were supposed to return the left and right split, right? But you see what we are doing here. We are calling the build tree function. What is the build tree function? That is this itself. So basically, you see what's happening. The build tree function is calling itself. So this is like recursively calling until one of these conditions are arrived, right? So this return will never finally get you out of this function. Only this return or this return will get you out of this function, because you have to return some tree node value in the return function. Instead, if you have a call to another function, you are going to that function. You are not going back to where this build tree function was originally called from. But see what we are doing. When you are calling the function, you are, which means you are splitting. You're going to split the node once again to create the children node, which means depth is increasing by 1. And so this is the current depth. Then max depth and min samples we already discussed. So this will build the tree again and again and again until it reaches either you have a pure leaf, or you have minimum number of samples reached for a node, or if you have exceeded the maximum depth. And then you have a function for making a prediction on a new test data set. So here the prediction is made at different nodes, right? So if it is a leaf node, there is a prediction. If it is a root node, there is no prediction, because a root node does not make, internal nodes does not make any prediction. Root node also does not make any prediction. So here in the predict tree function, you have node and the data point X in which features are there. You don't know the label because this is test data. And what you are going to check is node of nothing, is whether this is true or not. Is nothing of node dot feature, whether this is true or not. What does this mean? It means in here where we were storing the node, if feature is nothing, it means it's a leaf node. But if prediction is not nothing, then it's a leaf. Then also it's a leaf node, because if prediction has some value stored, it will be the mode of all the data points. So if mode is saying that the value is 1, it means majority of the data points in that leaf node is 1. So you have to predict the answer also to be 1. So you have to output prediction, whatever is the node, the value stored in this prediction you have to output. If it is a leaf node, if it is not a leaf node, you have to go until you reach the leaf node. So here you will return node dot prediction only if the node dot feature is empty, or if the value is nothing. Otherwise, if this condition is not true, what we are going to do is you will return x dot node feature less than or equal to, if you will check if the node dot feature or in the x, which is the input, whether that is less than or equal to threshold. If it is threshold, then you will try to make the prediction for that corresponding node to the left and same node to the right. So here what you are doing is, for every individual data point in x, it's only one data point and it has one feature. You are checking whether the feature value stored in node dot feature, because node dot feature is the best feature for that node, is the value of best feature for the data point x. Is that less than or equal to the value of the best threshold? Because node dot threshold stores the best threshold. If yes, if that is true, then the data point goes to the left. Otherwise, the data point goes to the right. So here predict tree, again, it's recursively calling itself until you are reaching the leaf. If you reach the leaf, then this function will return. If you don't reach the leaf, you are not going to predict yet, because you have to go to the node until you have to traverse the branches until you find the leaf. Only leaves can make the prediction. Please remember. Okay. Now here you have another structure. So this data structure was storing individual nodes. So this was for node. Now here you have one for trees, where you are storing the nodes within the tree. So here your individual nodes will be stored as one tree structure. And you will see that when you are calling this random forest function, you are passing maximum number of trees, or exact number of trees, maximum depth of each individual tree, minimum sample number of data points each node should hold. So when you call random forest function, these three things are passed. Then you have a function here which helps you build the subset of data. So you are sampling data sets from your big data. So your entire data set is X and Y. Let me take the pen. Your entire data set is X and Y. And from that, you are sampling data sets of certain IDs, and that you are storing in this X sample and Y sample. And using those X sample and Y sample and the depth of the tree, and this is the current depth, I guess. Current depth is 0. You are yet to start. And this is the minimum number of data points you need at a node. So you are calling the build tree function, and whatever is build tree function is returning, which is the tree itself with the collection of nodes, is being stored in the forest.tree, ith component of the forest.trees. How many components are there like that? How many ever number of trees are there in the random forest? So that will depend on length of forest.trees, and length of forest.trees will be defined somewhere later. We'll get to that. You have a prediction function also to predict the final verdict made by the random forest, and final verdict is obviously the mode of all the predictions made by the individual trees. So you need predictions, you need to store the predictions made by the individual tree. So predict tree function is called for every tree in the forest for the particular data which you are considering in the test data set. And then you can return the mode of all those individual predictions. That is this function. Now here, it's over, like random forest creation is over. Now we just need to create the data set, split them, and then call the random forest function. So you have the training data here with 100 data points. You have testing data with just 10 data points. And here you are calling the random forest. You are saying that you have 5 trees. Every tree should have maximum depth of 2. And every node should have minimum 2 samples, right? So 10 trees, max depth of 5, and minimum 2 samples per node. And then you are calling the this fit function. Fit function is this, where you are basically getting the nodes corresponding to every individual tree, and you iterate it over all the trees in the random forest. And your results are now ready, and now you can simply print all the things. So here I have written a function to print the individual tree structure in the random forest in a indented fashion. I will show you how this looks like. I don't want to go into the details of print. And then here you are calling the print function. This is just a function, and here you are calling it. And this makes the scatter plot visualization for making a plot that looks like this over here. Something that looks like this. All right. Now I think we are good to write the code. So I have opened Jupyter Lab, and I have already copy pasted the entire code here without splitting them into modules, because I have explained individual modules and individual functions, the code blocks in detail to you. So now all we need to do is let's just run this, and this should plot the data set. And the ideal output here should be, you should have a training accuracy, you should have a scatter plot of the training data, you should have a print of all the trees. So here you have 10 trees. And why is that so? Because somewhere I have mentioned 10 instead of 5. Yeah, here it's 10 trees, max depth is 5, and minimum number of samples per node is 2. If we change this to 5 trees, maybe it will look easier. So let me change this to 5. Maybe I'll get back to that. So here I'm printing all the trees, the structure. So you can read it in the following way. So for tree 1, the root node is the following. It's over here. So if feature 1 is less than or equal to 0.35, then you are creating 2 branches. So this is child branch on the left, and this is child branch on the right for the root node, right? And then for the child branch on the left, there is further split made. If feature 2 is less than or equal to this value, then you have child on the left for that and child on the right. Similarly, for the child created from the root node on the right, you have feature 2 less than or equal to minus 0.4. And then if that is true, you have child on the left, and child on the right is basically a root node, a leaf node, which is why there is a prediction. Similarly, for this, when you split, you have child on the left, but child on the right is a leaf. So this prediction, wherever you see predict, you can understand that that is a leaf node. Wherever you see feature less than or equal to something, it is a internal node. So this is how you can read the individual trees. It's a very complex way to display, but also not that hard to read. Then you have 10 trees, and let's look at the scatter plot. So this is your data, training data, and kind of you can see that it's very nicely getting classified into two categories. The way training data is created is using a random function. So you are creating, where is that? Yeah. So you are creating random samples. And we can also look at the final test data results. So test data is like this, and you can see that it's pretty much nicely getting classified because most of the points here should be blue. It should be in the category 0 and this should be in the category 1. Now what we can check is, and where is the test accuracy? Okay, training accuracy is 99%. I don't think we are plotting test accuracy because there are only very few points, only 10 data points, so no point in plotting. But what we could do is we could check the training accuracy if we had only 2 trees. So instead of 10 in the random forest, what if we had only 2? Number of trees is 2. Then maybe training accuracy should come down is what I am thinking. 97. What I can do is, what if it was 1? You don't have a forest, you only have a decision tree. So if it is 1, basically random forest becomes a decision tree. And here, okay, it's less, it's 96%. All right, this is good. I mean, if I have more mix of the data, which I can bring by zeros of 50 and ones of 50. So what I could do is reduce the value that is being added here. Okay, not in the testing, but in the training. So here, let's say it is plus 0.5. And this is also plus 0.5. How does the data set look like? I think there is a little bit more mixing now. And yeah, training accuracy decay. Okay, I think this is a perfect example. So here, look at this. My individual decision tree has training accuracy of 92%. Now, if I increase the number of trees in the random forest from 1 to 10, hopefully the training accuracy should increase. From 92, it should increase to something better. Let's see. Now we have 10 trees making the prediction. See, it is 97 now. So this is the advantage of random forest, because now if you have 10 different decision trees making a binary classification, the collective accuracy of those 10 trees will be definitely greater than the accuracy of any one individual tree. Individual tree had just 92% accuracy, but collective, it has now 97% accuracy. So I hope, although this video was a little bit long, I hope it brought a lot of clarity into the theory, implementation, and more things that you can learn in the future in the concept of random forest. I would, of course, like to make a lecture in the future about XGBoost in detail, but maybe I'll reserve it for a later time. But I really want to appreciate you for coming all the way till this part in this course, and special mention if you are also implementing all this in the code. So I know that it's not easy to follow all the lectures because you have to have a lot of commitment. And I don't think many people have that kind of commitment. They will start lectures or courses, but very few people finish. So if you are one of those very few who are diligently finishing all these lectures, I think you definitely deserve a lot of credit, and there is a long way to go. And I really appreciate you for that, and I definitely hope to see you in the next lecture. So thank you so much. We will see you again soon. Bye.